First of all, with the definitions of what a local max and a local min are, they're about the same as what you'd have in Calc 1. It's just that there's an extra dimension, kind of like a lot of other stuff in this chapter. Because if you look at what these are, it's the same concept, except that now rather than being in some open interval, you have an open disk, where then that way that would involve both dimensions. So if you think of the function as having independent variables x and y and dependent variable z, then the disk would involve both x values and y values, so both of those dimensions. But still, you think, well, then the local max is going to be a peak, right? It's going to be on the top of a shape, sort of, and then a local min is going to be on the bottom. And then this is just maybe to help a little bit with the visualization about the mountain peak and the valley bottom, this part here. Like with Calc 1, where if you have a local max, it's basically the top of the hump. It's just now that hump is three-dimensional, so it looks more like a mountain. It's that kind of thing. And same thing with the valley bottom. Now that's three-dimensional too. Then going back to Calc 1 again, when you have a local max or a local min, that's where the first derivative is equal to 0. Here, because we have two independent variables, you need both of the partial derivatives at that point to be 0. So partial with respect to x, and then down here the partial with respect to y. So similar idea, extra variable, so both partial derivatives instead of just the first derivative. And then definition of a critical point, again, about the same as Calc 1. Either where both of the partial derivatives are 0, or one or both of the partial derivatives doesn't exist, which I don't think that's going to be a thing that actually comes up in this section at all, but that is true. So might as well have the full definition instead of a half definition. And then the very last thing is if there is a local extreme value, either a max or a min at AB, then AB is a critical point, but it doesn't necessarily work in the opposite direction, where you could have a critical point where you get a local max, you could have one where you get a local min, or you could have one where you would have neither. The neither situation is kind of an interesting shape. We've seen it before, but we're going to see it again. It's an example number 2. For the first example, we want to find the local extrema, which is just a fancy word for see if there are any local maxes or local mins of this function up here, x squared plus y squared minus 2x minus 6y plus 14. So the first thing that you want to do is you want to see what points you would have where both partial derivatives are 0. So what I did was I took both partial derivatives, which here aren't too bad since this function is just a polynomial, and then where are we going to get local extrema? Well, you would need f sub x to be 0 and you need f sub y to be 0. So then I just solve those. And so basically what you would need was you would need x to be 1 and you would need y to be 3. So there's only one critical point, and it's the point 1, 3. Okay, so that's it. So then we just have to figure out, is that a local max or is that a local min? Well, the completing the square part down here is really just to kind of point out what kind of shape this is. So you have to complete the square twice. And if you do it, you get this thing, which is a paraboloid, more specifically an elliptical paraboloid, and it's one that opens up, right? There aren't negatives in here. So it's a paraboloid opening up, so that means that that critical point has to be at a local min. It would have to be at the bottom. And graphically, what that would look like is it looks like this. So there, where'd it go? There it is. That's that graph. So I made it in GeoGebra, and that's what it looks like. So yeah, it's a paraboloid opening upward. So then right down there at the bottom, that's where our critical point is. It looks a little bit off right now just because the way the axes are angled, and my computer gets too glitchy if I run this with the internet on, so I just have to kind of rely on this screenshot. But the z value there is 4, and it looks like it's lower just because the way the axes are tilted. But yeah, that's going to have to be a local min. So that's that first example. Second example, we're going to do the same thing to start off with, where we've got our function up here, f of xy equals x squared minus y squared. We want to figure out where the critical points are, if any exist. So you get the two partial derivatives, and then you say, well, the only place we'll get a critical point would be where f sub x and f sub y are both 0. So in order for that to happen, you would need x to be 0 and you would need y to be 0. So the only critical point is going to be the origin. However, this is the part that's kind of wild here, and this is where you get something different. Along the x-axis, y would be equal to 0, right? I mean, that for every point in the x-axis, that's the way that works. But then f of xy would really just be f of x0, and that's just x squared, right? Like the minus y squared you wouldn't have because you'd just be subtracting 0. But x squared is going to be positive when x is not 0, okay? But then what if you go the other way? You go along the other axis. If you go along the y-axis, x is 0, so then f of xy would reduce to f of 0y, and that's negative y squared, but that's going to be negative as long as y is non-zero. So what does that mean? Well, that would mean that any disk centered at the origin would have to contain values of f that are larger than 0 and smaller than 0. So that means that the origin is not the location of a local max or a local min. So what is it? What it is, the definition's actually down at the bottom. I'm going to go down to that first. It's something called a saddle point. And this definition looks like it's exactly what's going on, where you've got points where the function evaluated at that point is going to be bigger than f of ab, and you're also going to have points where the function evaluated at that point would be less than ab. And the shape that you get, this is actually one that we've seen before. It's this. So it's where here you can see this parabola shape opening down underneath when I've got the axes tilted sort of the conventional way. But then I've got another picture in here like that, where notice how now I've got the x-axis pointing like way off to the left and the y-axis like coming right at you. But then you can see this parabola here that's opening upward. So then you kind of get that effect where at the origin, any disk that you take that's centered at the origin, it's going to have points where you have a z-value less than 0 and points where you have a z-value greater than 0 because of those two parabola shapes that you get in there. So it's the thing that we called the saddle surface when this came up in chapter 12. And saddle surfaces have saddle points. So the saddle point graphically is just the thing that's right there in the middle of the saddle. So let me bring that picture back up again. Can't see it too well here. I guess you can see its underside here. Maybe with this one you can see it a little bit better. So yeah, saddle points. You're going to have a saddle point if you've got a saddle surface. And maybe that's one where just looking at the function you can see right away like, oh yeah, that's the thing from chapter 12. But this is the other option, where if you don't have a local max or a local min, you can have one of these. Okay, so with that first example, the one with the paraboloid, we figured out that it was a local min essentially by figuring out that it was a paraboloid. But what if your shape isn't that nice? How do you figure out if you have a local max or a local min or a saddle point, right? How do you do it? Basically, it's this stuff here. So this first definition, the determinant or Hessian of f, it's this determinant right here where you've got the second partial derivative of x with respect to x, then y with respect to y in those corners, and then partial of f with respect to x, then y, and then same thing down there. I guess technically the one in the lower left corner should be f sub yx, but no book ever writes it like that. And if you have a continuous function, f sub yx and f sub xy are going to be the same thing. So I guess that's why it always gets written that way. But then the determinant would end up being this, right? Because you would use the diagonals. So just like when you use the determinant when you're getting a cross product, right? Same concept. So then how does this all factor in? Well, this second derivative test for local extrema, and so that's saying, okay, f, the first partials and second partials are all continuous, And then suppose we have a critical point where here the partial of f with respect to x and partial of f with respect to y at a, b, both 0. So critical point. Then this is how you can tell if you're getting a local max, local min, or a saddle point. So if the determinant of f or the Hessian, when I took Calc 3, that Hessian terminology was being used, but I think that's sort of outdated now maybe. I'll just stick with determinant. So if your determinant is positive, you're going to get a local max or a local min. And then how you figure out which one you've got, it depends on what's going on with the second partial derivative with respect to x. So if you look at what's going on here, it's kind of like concave up and concave down, right? Like in Calc 1, where if you have a function where you're like, okay, here's the critical point, and then we get the second derivative and it's negative, then that's where it's concave down, and so then the critical point is at the top of the hump. So it's a local max. It's the same thing here, right? You get a negative second partial derivative with respect to x, you're going to get a local max. And then like in Calc 1, where if the second derivative is positive, then it's concave up, so a critical point has to be at the bottom of the valley. So same concept here, right? Second partial with respect to x, if that's positive, you're getting a local min. So those are the first two. Then if the determinant's negative, you get a saddle point. And then the fourth one, if the determinant is 0, you have an inconclusive test. That does not happen in this section. It's there in our book, and I threw it in just for completion. But that fourth option you really don't have to worry about, at least not for right now. Example number 3, where we're going to find and classify the critical points of this function here. So first, figure out where the critical points are. Get the two partial derivatives. Then we say, all right, well, the critical points are going to exist where both partial derivatives are equal to 0. So we would need 4x cubed minus 4y equal to 0 and 4y cubed minus 4x equal to 0. So then basically I just kind of simplified those a little bit. This is the first one simplified. Really, that's just saying that y equals x cubed. And the second one is saying that y cubed equals x. So then all I did to try to figure out where the critical points would be is that I subbed y equals x cubed into the other equation. So I just stuck the x cubed in for y. Then you get x cubed cubed equals x, or x to the 9th equals x, or x to the 9th minus x equals 0. That factors. So x to the 8th minus 1 is a difference of squares. So that's where I'm getting this part here, the x to the 4th minus 1, the x to the 4th plus 1. But then x to the 4th minus 1 is itself a difference of squares. So that's where I'm getting these pieces here. And then you say, well, the x squared plus 1 doesn't factor, the x to the 4th plus 1 doesn't factor. But x could be 0. And then from this, x could be 1 or negative 1. And that's kind of what I've got right there. So then I said, all right, if those are the x coordinates of the critical points, I also want the y coordinates. And then you can get the y coordinates just by subbing in to, I guess, either y equals x cubed or y cubed equals x. And you would get those 3 points right there. All right, so now that we know what the critical points are, we got to figure out what are they? Are they local maxes, local mins, saddle points? What's going on here? So you need these 3. If you take the second partial with respect to x, it's 12x squared. Second partial with respect to y is 12y squared. And then if you take the partial with respect to x and then take the partial with respect to y, you get negative 4. Okay, well then the determinant or Hessian, there's that right there's fxx, there's fyy, and there's fxy, and then there it is again. You get that determinant, it's 144 x squared y squared minus 16. So then we just have to check at the 3 individual points. So just substituting in, then at the origin, the determinant is negative. You get negative 16. So you say, okay, negative determinant, got to be a saddle point. So right away, you don't even have to check of what you would get if you subbed into the second partial with respect to x. Then the other 2 points, at 1, 1, you get a positive determinant because you'd end up with 144 minus 16, which is 128. And then the second partial with respect to x, you have 12 times 1 squared, so that's just 12. So then that's positive. So then that means that f of 1, 1 is going to be a local min. You get the exact same stuff here just because everything's squared, right? So subbing in negative ones is going to be the same thing as subbing in ones when you're just subbing into an x squared and a y squared. So you end up with the same determinant, same thing when you sub into the second partial with respect to x. So you're also getting a local min at f of -1, -1. So then I guess just to get the actual values, so the values of f, so at the origin it's 1. When you substitute in, that's going to be a saddle point. And then when you substitute in 1, 1, and -1, -1 at both of those, you get a function value of -1. So those are going to be both local minimums. With the word problems in this section, which is what example 4 and example 5 both are, I think the biggest strategic maneuver that you have to do is rewrite z in terms of x and y. Repeatedly that comes up. In the book problems, you have to do it in every single one, and it happens in both of these. So that's the biggest strategic move here. So we're trying to find the shortest distance from the point 1, 0, -2 to that plane. So the distance from any point x, y, z to 1, 0, -2 is going to be this, right? It's just the distance formula. But if x, y, z is on the plane x plus 2y plus z equals 4, then you can solve for z in terms of x and y, and then you can rewrite the distance in terms of x and y only. So that's the whole point of doing this, of solving for z in terms of x and y. So you get this distance formula right here where it just has an x and a y in it, because then you can treat that like it's a function of x and y, and then the stuff that we were just doing, how we were figuring out the critical points, and then if those are local maxes or local mins or saddle points, then that all works again. So instead of trying to minimize this because it has a square root in it, we'd end up with the same thing if we minimize d squared. All right, minimizing the square of the distance would also minimize distance. So we're going to do it like that just so it's a little bit less ugly. So the distance squared, which really is just a function of x and y, it's this, right? It's what's underneath the radical. So we'll do what we were doing before. We'll get the two partial derivatives, and then we'll see where they would be equal to 0. So the partial with respect to x, so I guess you don't need that middle term, but you need the first and third. So you take that partial derivative, simplify it a little bit, you end up with 4x plus 4y minus 14. And then you do the same thing for the partial with respect to y. You end up with 4x plus 10y minus 24. So critical points are going to exist where both of those are equal to 0. So, I mean, I guess you can solve it any way that you can see fit. You could set 4x plus 4y minus 14 equal to 4x plus 10y minus 24 if you wanted, since they're both equal to 0. That would be a logical move. What I did was I just took the first one and subtracted both sides of the second one, because then that way that would get rid of the x terms, so then I could solve for y. And doing it that way, I got that y was 5/3. And then I just subbed back into this one right here, and I rewrote 14 as 42 over 3 because I knew I was going to have to in order to solve this thing. So you end up with 4x equals 22/3, and then eventually x is 11/6 when you reduce it down. So the only critical point, it's 11/6 and then 5/3 for the two coordinates. All right, well then now we got to figure out what that critical point is. Is it a local max, local min, saddle point? So second partial with respect to x is 4, second partial with respect to y is 10, and then partial with respect to x, then y is 4. So let's see, we've got a positive second partial with respect to x, and the determinant is going to be 40 minus 16, which is 24. So that's positive. So then that's going to be a local min, right? Positive determinant, and then second partial with respect to x is positive. So according to the second derivative test, that's going to be a local min. And then to keep going, what is that local min? Like, what's the function value? What is that actual distance? If we substitute in, so subbing in the 11/6 and the 5/3, then eventually, you've got to square some fractions. You end up here, get a common denominator. You get the square root of 150 over 36, which is 5 radical 6 over 36 if you simplify the numerator, since that's 25 times 6 underneath the radical, right? That's what the 150 is. So the shortest distance, it's 5 radical 6 over 36. The next one, example 5, I'm going to do the same move as far as rewriting z in terms of x and y. So we're supposed to figure out the maximum volume of a box made out of 12 square meters of cardboard that has no top. So in my picture, that's why the top part is shaded in. That's supposed to represent that it doesn't exist. And then whatever our 3 dimensions are, so x, y, and z for now, then the volume is just going to be x times y times z, right? Length times width times height. So what we do know is that the total amount of material is 12 square meters. So when we add up the areas of the individual sides, we got to get 12. So we only have one xy, right? That's the bottom of the box, at least the way I have it arranged in the picture. And there's no top, right? That's why there's no 2 in front of this. But then we have 2 xz's and then 2 yz's. So the yz's, I guess, would be the left and right sides, and then the xz's are the front and back, right? And then when we add those 5 areas together, we would get 12. Okay? Well, then we can use this in order to solve for z. And using that, where z is 12 minus xy over 2x plus 2y, then we have a way to write z in terms of x and y, which means that then we could write the volume just in terms of x and y, and then we can do things the way that we've been doing them. So then here's that maneuver again, right? Rewriting z in terms of x and y. Computer got stuck for a second, sorry there. Okay, so then there, that's kind of what I was going after. The volume, it's a function just in x and y, so now it's x times y times that representation of z that's right here. And then I'm going to rewrite this a little bit. I'm going to pull that 1/2 out front just to make the partial derivatives easier, because there's going to be some quotient rule in this. So if we go down here, there's some quotient rule. So that's what the partial of v with respect to x is, and I use the Leibniz notation here just to kind of change it up a little bit, right? You could just write it as v sub x if you wanted to, but I wanted to get a little bit of variety in there. So yeah, quotient rule to get that partial derivative. Eventually you end up here. I factored out the y squared just to make it a little bit easier to see what part we won't have to deal with later, because y could not possibly be 0 if we're looking for the max volume, right? If y is 0, then one of the dimensions is 0, so therefore the volume is 0. That's definitely wrong. So I have it written this way to isolate that y squared to then be like, okay, we just got to worry about this part right here. So that's the only reason I wrote it like that. And then if you do the same thing with y, so you take the partial of v with respect to y, you get a very similar looking thing, just with the x and y's in the opposite spots. So you can go through and do it if you want, but it's very repetitive. And then critical points. So the partial with v with respect to x, that could be 0 either when y is 0 or when this expression is 0, but y can't be 0 because then we get a 0 volume and we're looking for a max. Max isn't going to be 0. And then same thing with the partial with respect to y. It's not going to be when x is 0. So we're going to just have to worry about the other piece. So the 12 minus y squared minus 2xy. So we need 12 minus x squared minus 2xy and 12 minus y squared minus 2xy to both be equal to 0. I did the same thing and just said, well, then if I subtract the second equation from the first, we're going to eventually get that x squared is y squared, which would mean that x is y in this, I guess, in this context, because x and y can't be negative, so you don't have to worry about the negative square roots, right? They're dimensions of a box. They're not negative, so you don't have to worry about that part. And I guess right from here, you could say, well, if you just set those equal to each other, almost right away you get the x squared equals y squared. That's true, and if you wanted to do it that way, then you're more efficient than me. But then knowing that x equals y, if we sub in, so I subbed in right there for y, I subbed in an x, and then you can solve that, and eventually you get that x is equal to 2. All right, well then if x is 2, then subbing back into, I think I subbed into this one right here, you'd end up with that y is also 2. But then if x is 2 and y is 2, then we have that expression for z in terms of x and y. We sub in there, we get that z has to be 1. All right, well, you could use the second derivatives test here, and that would show you that this is where you'd get a local max for the volume. But since this is a physical problem, there has to be a maximum volume, and the only place that could occur would be a critical point. And since we only have one critical point, it seems like it would have to be that, right? Because it's not going to be a minimum, right? That wouldn't make any sense. The minimum is clearly 0. And the way that this function's set up, you couldn't get a saddle point. So you could kind of reason your way through it too without using the second derivatives test. Either way, what the max volume is going to be, it's just 2 times 2 times 1, which is 4 cubic meters. Those last two examples were kind of long, but this sadly is going to be even longer. And that's because when you're looking for an absolute max or an absolute min, you have to check the entire boundary, and that usually takes a long time. The interior part's usually really fast because that's what we've been doing, and you don't really get a whole lot of critical points, and that's not too bad, but the boundary takes a while. So basically what you do, if you're trying to get the absolute max and absolute min on a closed bounded region, is, and the main concept is, in addition to the critical points, because those are going to be in the interior, you also have to check the entire boundary. So it's kind of like in Calc 1, where if you're looking for an absolute max or an absolute min on an interval, you check the critical points and you check the endpoints, right? But now, because we have an extra dimension, it's not that there are just endpoints, it's that there's this boundary, which maybe that's shaped like a triangle, maybe that's shaped like a rectangle. That actually involves a lot more work than it used to. So it's the same concept as Calc 1, it's just the thing that's the boundary is more complicated. So the best thing to do is just to make a list. So figure out what the critical points are, and then you evaluate the function there, put those in the list. Then you check the boundary, look for extreme values there, and the extreme values that you get on the boundary, put those in the list too. What you'll probably have to do with the boundary is break it down to individual pieces. Like if it's a triangle, you do each side of the triangle. If it's a rectangle, you do each side of the rectangle. But then once you have that whole list put together, then the largest function value is the absolute max and the smallest one is the absolute min. So then that part's easy once you got the whole list. It's just that getting the whole list takes a while. I don't know that I would necessarily say that it's hard, but this has the potential to be long. And I think there are a couple of these in the problems from section 14.7. There's a triangle one and a rectangle one. I wanted to put a rectangle one in here because that's the one that's slightly longer. Like if you can do the rectangle, you can do the triangle, because the triangle only has 3 pieces. This has got 4. So we're going to try to find the absolute max and min values of this function on the rectangular plate defined this way, where x is between 0 and 3 and then y is between 0 and 2. So do the interior first. We already know how to do that, so we'll go ahead and get it. That's where you just look at the critical points and evaluate the function there. So you get the 2 partial derivatives, and then the only critical point there is going to be 1, 1, because in order to get f sub y to be 0, x clearly has to be 1, right? And then you say, well, then if x is 1, then to get the partial with respect to x to be 0, y's also got to be 1, so that's the only critical point. You evaluate the function there, and you end up getting 1 as a function value. And I just put that double asterisk in there to remind myself, put that on the list later, right? That goes on the list. That's the function value for our 1 critical point. Now the long part. So the boundary, it looks like this. It's a rectangle, so right from the origin to 3, 0, and then going up 2, right, origin up to 0, 2, and then you'd go over to 3, 2, and that should give you that rectangle. And then I just labeled these as L1, L2, L3, and L4, just so that way I have like a way to organize this. And I can say, all right, we'll do L1, and then we're actually going to do L3, and because those are similar to each other, and then do L2 and L4 after that, because those are similar to each other. All right, so on L1, so on the left side, x is equal to 0, which means that the function, instead of being f of xy, we could just write it as f of 0y, and then if we put zeros in for x's, all you're really left with for the function is 2y. And then generally, like without using anything extra, so avoiding the cloud over here for now, I'll come back to that in a second, but if you just check the endpoints of that line segment and then look at the interior, that will always work. So I check the two endpoints. So f of the origin, you get 0, and then f of 0, 2, so the upper endpoint of L1, right, up there, you get 4. And then the interior, if you look for critical points, it's just going to be a regular old first derivative where y is your independent variable. But if you take that first derivative, you just get 2. So that doesn't have a critical point, right? There's no way you could possibly get 0. So then these are the only two that you would add to the list. Alternatively, if you're looking for the max and min along that line segment, you could say, well, 2y is always increasing, right? As y increases, 2y increases. So that means the minimum has to be where y equals 0 and the max is where y equals 2 on that line segment. That does work. So you can reason through it like that as well. So that thing that's inside the cloud, that's another way that you can essentially get the same answer. Then if we do L3 next, it works just like L1, except that x is equal to 3 instead of 0. So there's L3. X is equal to 3, so you sub 3 in for x, where it shows up in the function, you eventually get 9 minus 4y. If you check the two endpoints, f of 3, 0 is going to be 9, and then f of 3, 2 is going to be 1. And then if you take the derivative with respect to y, you just get negative 4. So no way for that to be 0, so no critical points. Alternatively, you could say that as y increases, 9 minus 4y is always decreasing. So you would have to get the min and max at the endpoints, right? You're going to get the max when you have the lowest value of y, so at 3, 0, and then you're going to get the min at 3, 2. Right? Either way, if you want to reason through it like what's in this cloud, or just do the endpoints and then look at the interior, even though here the interior doesn't give you anything extra, that would work either way. Then L2 and L4. Okay, here's L2. So L2 is the top, where y equals 2. All right, well then, if y equals 2, you can sub in 2's for y's, and then f of x2 is going to be x squared minus 4x plus 4. We already checked the endpoints, so you don't have to check them again. And this, if you have a rectangle, this is the maneuver that I kind of prefer because it feels like you do a little bit less work. If you do two opposite sides first in their entirety, you'll get all of the corners of the rectangle basically already covered. And so then when you do the second pair of sides, you really only have to check their interiors. So you could check the endpoints again if you wanted to. It wouldn't hurt, but it's just going to give you stuff that you already have, right? Like we already know these things. We got this, one of those from L1, the other one from L3. So then if you check the interior, so taking the derivative of x squared minus 4x plus 4, you get 2x minus 4. That does have a critical value of x equals 2. So then you just figure out, well, what do you get for f when x equals 2? So f of 2, 2 would be 0. Okay, well then there's something to add to the list, right? That's a new thing. And then lastly, the bottom, L4, that's where y equals 0. So if we sub in zeros for y's, we get that f of x 0 just be x squared. We already checked the endpoints, and again, you could check them again if you wanted to, but you won't get anything new. And then to check the interior, take the derivative with respect to x, you get 2x, right? And then the critical value would be when x equals 0. So, all right, well, f of the origin is 0. We did already know that, but it's worth checking, right? Just every once in a while you do get repeats doing this. That's fine. There's nothing wrong with that. Right? You just want to make sure that you catch everything, and in that process, you might get repeats somewhere. So then the summary. So here's the list. This is the list of everything that we got, right? So that f of 1, 1 equals 1, that's from the very beginning. That's from the interior. And that's the only one from the interior, right? Because then we got these two from when we did L1. We got these two from when we did L3. And then this last one came from L2. And then L4 didn't really give us anything new, right? It gave us this guy again right here. But then you just look through those and you pick out the largest and smallest values, and that's your absolute max and absolute min. So the biggest function value that shows up here is 9, so that's the absolute max. The smallest one is 0. Two different points give us that. We get it at the origin, and we get it at f of 2, 2. So then there's the absolute min of 0.